Hello everyone, I am Dr. Dilip from Vali Rameshwar'S Ias Academy, and today we are going to discuss a topic that is the gravitational wave, which is a part of science and technology. So to begin with a little bit about our institution. Our institution Vali Rameshwar'S Ias Academy is situated in Hyderabad, that is in JNTU, and we offer both online and offline coaching. And you can avail the online coaching right now, as offline coaching has been affected with the ongoing pandemic of COVID-19. And our online coaching starts at a cost of rupees 15,000 only, where it covers UPSC prelims at 15,000, TSPSC Group 2 at 15,000 and APPSC Group 2 at 15,000. You can also download our app on Play Store, that is Vali's the Learning app. And you can reach us at www.valirameshwar'sIasacademy.com, and you can even call to these numbers if you have any queries. To begin, to talk about the topic proper, the first, what is gravitational wave? The definition itself. So a gravitational wave can be defined as ripples in the fabric of space-time caused by some of the most violent and energetic processes in the universe. So what is this ripples? You have to understand what are meant by these ripples and what is meant by this fabric of space-time. And it is said that these are caused by the violent and energetic processes which happen in the universe. So ripple is basically a disturbance created in a medium, that is, especially if you try to understand that if you take an example that if you throw a small stone or a pebble into a standing water body, that is say a pond or a lake, it creates a lot of waveforms which are nothing but called as ripples. And here similarly this gravitational wave is similar to those ripples, but these ripples, as you have seen, the pebble has created on the water body, but rather this gravitational wave is created as waveform when there is a disturbance that is created in the space-time fabric. So what is the space-time fabric about? So if you see the space-time, so it is like a fabric, a sheet of cloth which is totally spread, onto which the planets or the stars, the luminous and non-luminous body or different bodies of the cosmos are placed. So for you to understand, let's take an example that let's see a trampoline. A trampoline is a device or an instrument onto which individuals can jump, and once they exert pressure, it is going to again throw them back or push them in an opposite direction. So that is a trampoline. So if you take a trampoline, and normally the trampoline appears to be stationary or there is no deformity, but you take a small object which is in the shape of a sphere or spherical, and if it is kept on the trampoline, so naturally what happens is the trampoline, which is usually having the plane surface, because of the weight of the body, will slightly bend at the center where the body is resting. So this is nothing but like a disturbance that is created in the fabric of the trampoline, which can be compared with the disturbance in space-time. So here assume that whenever this body or the sphere is moving on a continuous basis, so automatically it is going to change the way this surface of the trampoline is going to bend. So if this body moves in this direction, the bending nature also will slowly move to this aspect. So initially the bending nature is here. As the body moves in this direction, it will continue to deform, that is the bend will move on, and as the body moves, the deformity continues changing. So this change is nothing but, if taken into consideration here, is generating the ripple like thing, which is nothing but called as the gravitational wave. So here, why are we talking about the space-time fabric? So you can simply understand that space, so this is nothing but an area on the trampoline. Assume that this trampoline is present in the universe, a big trampoline on which all the celestial bodies or different bodies of the cosmos are present. So that will be nothing but the space. Then what about time? How can time vary? So you know the simple concept, that is speed is equal to distance by time. So speed is equal to distance by time. So whenever we are talking about light and light traveling in vacuum, that is the velocity of light in vacuum, that is c is equal to 3.8 into 10 power 8 meters per second. So this is constant when we talk about light traveling in vacuum. So the velocity of light, if you see here, which is denoted as c, that is nothing but the speed, and speed here is constant. So speed is constant, and then so here time is also directly proportional to distance here. So if you see a normal path of light, if it takes the same path, that is there is no curvature of the space-time fabric as such because of the planet moving, then like if you can see the flat surface of trampoline, the distance covered will be constant. But if you see if the body, spherical body or a planet is present on the space-time fabric, there will be certain curvature leading to increase in the distance traveled by the light. So light here is going to come in a straight line. Because of the bend in curvature of the space-time, it is going to bend and again move. So as distance is increasing, so light traveling in a straight line here, and here distance covered is also increasing. So automatically as distance increases, then the time also changes. So here you can see that because of the distortion in or increase in the curvature of the space, automatically time is being affected. Hence, you can call it as space-time fabric. So here any disturbance that is created in the space-time fabric, that is the surface of a trampoline, for you to understand, that is here if a spherical body is present here and the spherical body is keep on moving like a blanket of fabric, then if that body moves, automatically it is going to drag the fabric from beneath it. So this disturbance, whatever that is there, it is going to move forward in the form of ripples, which are known as gravitational waves. And this gravitational waves concept was not new. It is not new. It has been first brought into light by Albert Einstein through his theory of relativity. Theory of relativity. So we are going to go back so that to understand the things. So gravitational wave is usually created when some of the most violent and energetic processes occur in the universe. So what are these violent and energetic processes? So these are the processes where, for example, when two black holes merge, when a neutron star and a black hole merge, so there is a significant disturbance that is going to be created in the space-time fabric, which will lead to development of ripples, that is nothing but disturbance, which will be generated in the form of gravitational waves and will move to large distances. So here you can see when a massive object collides with another or changes speed or direction, it produces waves in the fabric of space-time called as gravitational waves. So here you can see Earth, it is also present in the space-time fabric. So because Earth is present, so you can see that the space-time fabric is undergoing certain curvature, and similarly all the planets or the stars will lead to certain curvature in the space-time fabric, and when they undergo significant changes, that is changes in the motion or any other explosion, it will lead to disturbance in this space-time fabric, which can be seen as production of ripples. That is nothing but it will lead to generation of gravitational waves. So moving on, you can see here Albert Einstein predicted the existence of gravitational waves in 1915 in his theory of relativity. Einstein's mathematical model showed that massive accelerating objects such as neutron stars or black holes orbiting each other would disrupt space-time in such a way that waves of disrupted space would radiate from the source like a movement of waves away from a stone thrown on a pond. So furthermore, these ripples would travel at the speed of light through the universe, carrying with them information about their cataclysmic origins as well as invaluable clues to the nature of gravity itself. So whenever a gravitational wave is generated at a point, it continues to travel large distances, and thereby if at all you try to detect or you can detect a gravitational wave, you can understand that there is some great change, that is explosion or an event that has led to the creation of these gravitational waves. So here you can see in the image that Hubble measures deflection of starlight by a foreground object. So if a white dwarf, which is in one of the positions in the life cycle of a star, is taken into consideration, and here this is the Hubble telescope which is present in the space, and it is trying to make an observation of a star which is very close or moving in the path of this white dwarf. So what happens is, this white dwarf is going to create certain disturbance in the space-time, and because of this disturbance it will lead to certain curvature, a change in curvature of the space-time fabric. So when the star is traveling close by, it is also going to go through the curvature, thereby leading to deflection of its actual course. So when observed, it appears that the star's position is this, but in actuality the star's position is far away. So this difference is because of the gravitational wave coming into force. Then moving forward, the strongest gravitational waves are produced by catastrophic events such as colliding black holes and collapse of stellar stars core, that is supernova, coalescing neutron stars or white dwarfs. All these are different stages in the life of a star. So here gravitational wave observatory, one of the observatory of gravitational wave has first detected a notable observation of gravitational wave on September 14, 2015, and that observatory is LIGO, which is called as Laser Interferometer Gravitational Wave Observatory, which physically sensed the distortions in the space-time caused by passing gravitational waves generated by two colliding black holes nearly 1.3 billion light years away. So they have calculated the distance of these black holes by understanding the intensity of the gravitational wave what they have recorded, and LIGO's discovery will go down in history as one of humanity's greatest scientific achievement. So when Mr. Albert Einstein, the greatest scientist of the mankind, has given out his theory of relativity, which indicates that the space-time fabric can be distorted, people did not give proper emphasis and his achievement was not noted. But this observation has proved that gravitational waves existence has proved that this Einstein's theory of relativity is really indeed true. Then moving on, so even though the gravitational waves are created at a faraway places, that is several million light years away, only the gravitational wave can be sensed from it, that is only in a minute quantities. So you don't have to worry that this disturbance of space-time fabric is going to significantly impact Earth. So here why it is lucky for us here on Earth, while the process that generate gravitational waves can be extremely violent and destructive, by the time the waves reach Earth they are billions of times smaller. In fact, by the time gravitational waves from LIGO's first detection reached us, the amount of space-time wobbling they generated was thousands of times smaller than the nucleus of atom. Such inconceivably small measurements are what LIGO was designed to make. So here assume this two black holes binary hole, that is two black holes are there, they are rotating around each other, and because they are moving, what is happening, they are creating disturbance in the space-time fabric, and because of that ripples are generated, and the disturbance in the space-time fabric itself is called gravitational waves. And if there is some major event, more disturbance is created and significant gravitational waves will be produced, and they are going to reach to the far end places of the universe, which can be detected by this observatories such as LIGO. Then moving forward, so what is this laser interferometer gravitational wave observatory? So this LIGO is the world's largest gravitational wave observatory. It comprises two enormous laser interferometers located thousands of kilometers apart, and LIGO exploits the physical properties of light and of space itself to detect and understand the origin of gravitational waves. So here you can see in the image, a laser light is used to generate a single color light. So because laser light is characteristic of having monochromatic light, and whatever light that is produced from the lasers has a significant other feature, that is the light remains in phase. So when this light is being sent, it is sent to a beam splitter which splits the light into two axes. One is in the same axis of the production of the light by the laser, and another 90 degrees to the axis of production of light. That is, assume that it is in x-axis and y-axis. So once that beam splitter is splitting the light, an equal arm, that is light, travels both aspects 90 degrees angle towards a length of 4 kilometers. So here 4 kilometers, and in the other direction also it travels 4 kilometers. And upon reaching 4 kilometers in two directions, what happens? At the end there is an end mirror placed. So at this end mirror, again the light is going to be totally reflected. So again it is going to travel in the opposite direction to reach the beam splitter and way beyond the beam splitter. So because the light is being reflected totally, the phase remains unchanged. But here when the light is returning back, they remain in opposite phases. And when they come to this detector, so near the beam splitter, they will be present in opposite phases. If there is no disturbance, or if this length 4 kilometers and 4 kilometers of the two arms of the LIGO observatory are fixed, then what happens? Because the length is same, the phase difference will remain the same, and two waves will undergo interference. And here the interference, what that you can see is destructive interference, leading to the total cancellation of amplitude of the two waves. Subsequently, the waveform will be totally cancelled, leading to no detection of light at this point, and hence in the photodetector there will be no light detected. So if at all there is a gravitational wave, here what happens? The gravitational wave is going to distort the space-time fabric. So once it is distorting the space-time, automatically here the length of the two arms, though they are made up of concrete bodies, yet they will undergo a very minute change of some micrometers or so, and this will change the phase once again. And though the two waves will interfere at the point, what happens is there will be no total cancellation of the two amplitudes of the waves. Subsequently, certain amount of light will be detected by the photodetector, which indicates that the gravitational wave is present or has been detected. So moving on, we will see what are the characteristics. So here, though LIGO's mission is to detect gravitational waves from some of the most violent and energetic processes in the universe, the data collected may have far-reaching effects on many areas of physics, including gravitation, relativity, astrophysics, cosmology, particle physics, and nuclear physics. So because the understanding of the universe is not yet total, this gravitational waves can help in understanding far more different arenas of physics itself. And there are few characteristics of this LIGO observatory. So three things distinguish LIGO from traditional astronomy observatory. So what are those? See, if at all you talk about the traditional astronomy observatory, that will include your optical observatories, that is, which will depend upon the electromagnetic radiation, and also you have the plain observatories, which are nothing but the radio wave observatories, which will take in the radio waves and again which will transmit the radio waves. See, what are the difference when we compare those traditional observatories with that of LIGO? So LIGO is blind, first one. So we will see why it is blind. LIGO is not round. So most of the traditional observatories which will take in light are round in shape, and a single LIGO detector cannot confirm gravitational wave on its own. We will see why that is in the next slide. So moving on, why LIGO is blind? So unlike optical or radio telescopes, LIGO cannot see electromagnetic radiation. So here gravitational wave is not part of electromagnetic radiation. If you see electromagnetic radiation, you have various type of radiations present in the spectrum of ER, and that will include the radio waves, microwaves, and moving forward you even have the X-rays, and you have the visible spectrum, infrared radiations, ultraviolet radiations, alpha, beta, gamma radiations. But in all this spectrum, if you can clearly inspect, there is no scope of having gravitational waves, because gravitational waves are not a part of electromagnetic radiation, and their characteristics also differ. So if at all you want to observe electromagnetic radiation, you need certain opening or aperture so that you can capture the light or electromagnetic radiation. But here, because you have no necessity to capture electromagnetic radiation, LIGO is said to be blind. So here we will see electromagnetic radiation, which includes microwaves, radio waves, and visible light. And here that is LIGO does not, or it doesn't have any requirement, because gravitational waves are not a part of electromagnetic radiation. In fact, electromagnetic radiation from space is so unimportant to LIGO that its detector components are completely isolated and sheltered from outside world. That is why you can see the arms of LIGO, which are present at a length of 4 kilometers, are totally covered in steel, and inside of it is present in vacuum sealed environment, and it is covered by concrete. And here the next point, we have understood why LIGO is blind, because there is no opening aperture. Then coming to the second thing, LIGO is opposite of round. So why it is opposite of round? As you can see, the shape of LIGO, which is L shaped, that is two arms of LIGO will make it L shaped, comparing to the conventional observatories. So if you see the radio wave observatory, it is like a semilunar position and it will transmit the waves. And if you see optical, they are round in shape. So compared to this two, the shape of LIGO is totally opposite. So since LIGO doesn't need to collect light from the stars, it doesn't need to be round or dish shaped like optical telescope mirrors or radio telescope dishes, both of which focus on electromagnetic radiation to produce images. And each LIGO detector includes two arms which are 4 kilometer long, 1.2 in diameter steel vacuum tubes arranged in L-shaped and covered by a 10-foot wide, 12-foot tall concrete enclosure that protects the tubes from environment. So here you can see the images. So this is the LIGO, and in LIGO or any gravitational wave observatory, you can see the shape. Each arm is 4 kilometers wide, and the shape is rather unconventional, and they are covered by concrete. And rather here you can see the radio wave observatory or detection center, which is a dish shaped. Then moving forward, and the last one, a single LIGO detector cannot confirm gravitational waves on its own. So why is this? So if at all there is certain disturbance because of an earthquake or a movement of tectonic plates or certain fissure or in the surface of Earth, which will lead to a disturbance, that the length of one of the arms of the LIGO detector can be changed in minute, that is few millimeter or less than few millimeters. And if in the case, what happens, the light that is returning from the reflectors will not have the same phase, will not be in exactly opposite phase as that in the normal condition, and when they superimpose, what will happen, there will be certain amount of light that will be detected at the at the photo detector, and by this what happens, there is a false positive that people will think, or the scientists may think, that they have successfully detected a gravitational wave, but in reality that is a false positive. Then how can you check to certain false positive, which come in case of this gravitational wave detectors. So what can be done? We'll see. So while an astronomical observatory can function and collect data just fine on its own, gravitational wave detectors like LIGOs cannot operate solo. The only way to confirm a gravitational wave detection is by operating in unison with other detector. So as you can see, if you talk about the optical observatories or radio wave observatories, a single observatory can do the work, and there can be a accurate identification of whatever observation that is done. But in case of gravitational wave, because there is chance of false positives, you always have to see that this observation, whatever that is done at one observatory, be confirmed by the observation done at other observatory also. So these observatories will never be present in single. So it indicates, or it signifies that the gravitational wave observatories will always be present in number of twos. So here you can understand this ensures that local vibrations are not mistaken for gravitational waves. A single detector can in principle sense a gravitational wave, say from a supernova explosion, but to confirm the detection, a coincident electromagnetic signal of some kind would also have to be made, again verifying that the LIGO detector sensed was not just some random noise in a single detector. So these are the three characteristics of LIGO. What are those? First one is LIGO is blind. Second is LIGO is not round. Third one is a single LIGO detector cannot confirm gravitational waves on its own. Then moving on, what is meant by wave interference? So LIGO observatory or gravitational wave observatories usually use this wave interference. So interference is a phenomenon in which two waves superpose to form a resultant wave of greater, lower or same amplitude. So this wave interference, that is nothing but when two waves superimpose, that is they come one on the other, then what is happening? The resultant wave, because of these two waves, can lead to formation of a new wave which will have an amplitude which is greater than the original two waves, less than two waves, or equal. So here you can see wave interference again is two types. One is constructive interference, second is destructive interference. So if the waves are almost in the near same phase, that is if the crest of one wave excuse me, that is if the crest of one wave falls on the crest of another wave, that will lead to constructive interference. Constructive interference. Then if the crest of one wave falls on the trough of another wave, it will lead to destructive interference. Destructive interference. So here you can see when in phase, if two waves, that is the trough of one wave falls on trough of the other, crest of this wave falls on the crest of the other wave, leading to constructive interference. And if the two waves are out of phase, that is if they are having a phase difference of 180 degrees, then it will lead to destructive interference. So what is meant by phase? Phase is a definition of a position of a point in time on a waveform cycle. A complete cycle is defined as 360 degrees of phase. Then moving on, so here what will happen is, in the absence of a gravitational wave, as the distance between the mirrors is same, it will lead to destructive interference, cancelling each other. So near the photo detector, no light will be detected, and in the presence of a gravitational wave, as it distorts space and changes the distance between mirrors, the distance keeps on changing. Therefore superposition changes. By measuring the intensity of light that is reaching the photo detector, the strength of the gravitational wave can be measured. So here what happens, because of the change in the length of the arms of the LIGO, automatically it will lead to the superposition in such a way that they are not totally cancelled, and it will lead to a resultant detection of light at the photo detector. So here assume that in this image you can see two black holes which are moving or rotating around each other like a binary black hole system, and because of their movement you can see the disturbance that is created in the space-time fabric. That is nothing but the generation of gravitational wave. This gravitational wave slowly from the universe at certain place will slowly keep on moving towards the gravitational wave observatory, which is having two arms. And here in this, the laser is being produced, and the laser light is being split into two parts by the beam splitter, and it is sent at opposite directions, that is at an angle of 90 degrees by each other, and they go at the end of the arm, that is at 4 kilometers apart in each arm, and they reach a mirror where they are again reflected back, and when they are reflected there will be a phase difference of 180 degrees. So that is meant by that they are in totally opposite phase, and when they superimpose automatically here, normally if this black hole is not creating a gravitational wave, they should totally nullify each other because of destructive interference. But because of the non-cancellation of the two waves that are coming back, that is light waves, because gravitational wave has distorted one or both the arms of the observatory, that is gravitational wave observatory, it will lead to certain disturbance that is created, and they will not totally end up in destructive interference, and certain amount of light can be detected at the photo detector, leading to a positive observation of gravitational wave. Then gravitational wave observatories around the world. So in all across the globe you can find various types of gravitational wave observatories. So first we are going to see one by one. Tama 300 or Tama 300 in Japan, Clio also in Japan, Kagra in Japan. So all the first three are in Japan, Tama, Clio and Kagra. Then Virgo is the gravitational wave observatory in Europe, Ligo in USA, Geo 600 in Germany, Mini-Grail in Netherlands, and IndiGo or Ligo India is said to be going to be stationed or started in India. This is all about the gravitational wave observatories across the world. Then moving on, when was the first observation of gravitational waves done? So first observation of gravitational waves. So the first observation of gravitational waves was made on 14 September 2015 and was announced both by Ligo and Virgo collaborations on 11th February 2016. So here you can see, though the observation was done on 14 September 2015, it was made public on 11th February 2016 because the two observatories, gravitational wave observatories, that is Ligo and Virgo, Ligo situated in USA and Virgo situated in Europe, had shared their observations, and they have confirmed, and it has taken certain time, that they can openly and strongly come to the public and give out a statement that yes, indeed gravitational wave has been observed. So previously gravitational waves had only been inferred indirectly via their effect on timing of pulsars in binary star system. There was no solid physical evidence to prove the existence of gravitational waves. So the waveform detected by both Ligo observatories, that is here Ligo observatories in USA are 2 in number, Virgo in Europe are 2 in number. So here whenever we talk about any gravitational wave observatory, we have seen that a single gravitational wave observatory is of no use. So whenever a gravitational wave observatory is constructed, it is constructed in number of 2s. So here detected by 2 Ligo observatories matched the predictions of general relativity for a gravitational wave emanating from inward spiral and merger of a pair of black holes of around 36 and 29 solar masses and subsequent ring down of the single resulting black hole. So what happened, by this gravitational wave which was observed on 14 September 2015 has been generated because of merging of two black holes which are at the size of 36 and 29 solar masses, and the resulting gravitational wave that was observed was named as GW 150914. So this GW is nothing but gravitational wave. 15 is the year 2015, 09 is the month September, 14 is the day on which this observation was made. So if at all in exam you come across GW 150914 refers to it is nothing but the first gravitational wave observed by mankind. Then moving on, so IndiGo or Ligo India, which is a mega science project. So It is a planned advanced gravitational wave observatory to be located in India as a part of the worldwide network, whose concept proposal is now under active consideration in India and the USA. LIGO India is envisaged as a collaborative project between a consortium of Indian research institutions and the LIGO Observatory in USA, along with its international partners. So basically, Indian scientists or also in Indian institutions want to have the knowledge about the observations that are made in the LIGO observatories. So for that, this consortium of Indian research institutions are getting into a collaboration with the LIGO Observatory of USA so that they can be benefited. So LIGO India received the Indian government's in-principle approval in February 2016. Since then, the project reached several milestones towards selecting and acquiring a site and building the observatory. And if you talk about the LIGO India detector, it will be funded by the Department of Atomic Energy and the Department of Science and Technology. So basically, it will increase the sensitivity and international gravitational wave network and produce many-fold improvement in the localization of resources. That is the aim of having LIGO India project. So this LIGO India project is being carried out by a consortium of Indian institutions, research institutions. We'll see what are those. So once again, IndiGo stands for Indian Initiative in Gravitational Wave Observations. So it is a consortium of Indian gravitational wave physicists which is located, this IndiGo is located at Aunda, which is present in the Hingoli district in Maharashtra. So three lead institutions are present in the IndiGo consortium. So what are they? First one is IPR, which stands for Institute of Plasma Research. So as you know, the matter can be present in different states. So the normal states are solid, liquid and gases. Apart from that, you have a plasma state. So the research on plasma, where all the particles of the matter is going to be present in subatomic state, that is as protons, electrons and neutrons, then that state is called plasma state. So here the institute which carries out research on plasma of India is called as Institute of Plasma Research, which is situated in Gandhinagar, Gujarat. So this actively take parts in and is one of the member in the consortium. Then the next one is IUCA, that is Inter-University Center for Astronomy and Astrophysics, which carries out research on astronomy and astrophysics and is situated in Pune. And the third one is RRCAT, which is called as Raja Ramanna Center for Advanced Technology, which is situated in Indore, Madhya Pradesh. So all these three institutes have formed a consortium of Indian physicists who are going to collaborate with LIGO USA to be benefited by the observations and to localize the resources that are needed for setting up a gravitational wave observatory even in India. And moving on, the life cycle of stars. So here you have to understand, we have talked about the black holes, we have talked about neutron stars, we have talked about binary stars. So you have to understand what are these. So for you to understand, you have to come across the life cycle of stars. So all stars begin life in the same way, that is, they are formed by the accumulation of gas and dust. So a cloud of dust and gas, also known as nebula. So this term is important. So it all begins with a nebula. So this nebula will then become a protostar. That is nothing but it will come together to form a small structure which is called protostar, which goes on to become a main sequence star, and following this star develops into different ways depending upon their size. So as you can see, the nebula, which is nothing but dust and cloud, will then lead to the formation of a protostar. Then the main sequence will start. So depending upon the size of the dust or the protostar, they will further lead to different formations. So here, if the size of the star is same as that of the sun, then it will lead to formation of a red giant star, then a white dwarf, and then a black dwarf. If the size is much bigger than that of the sun of our solar system, then it will lead to a red super giant star, from there a supernova, and it may further end up into a black hole or a neutron star based upon the initial mass of the star from which the beginning has started. So we will see the definition of few of the terms here. So what is meant by black hole? A black hole, it is a region of space-times exhibiting strong gravitational effects that nothing, even particles and electromagnetic radiation such as light, can escape from inside of it. So as you can see, the Newton's definition of gravitation is quite different from the understanding of the gravitational wave put forward by Albert Einstein in his theory of relativity. So here black hole, what happens is it has intense gravitational force, that is nothing but gravitational effect will be strongest inside a black hole such that no radiation or whatever that is generated nearby it will be sucked deep inside it. At the same time, it will not allow any of the radiation to escape from it. So from a black hole, what happens is, if at all you want to make an observation and you want to prove the existence of a black hole, you cannot prove because it is not visible. As for any object to be visible, you have to make any observations from the light emanating from it. As no light is emitted or no radiation is coming from a black hole, you cannot make any observations. So thereby which you cannot prove that a black hole exists. But there is only way by which you can prove a black hole exists, that is by detecting a gravitational wave. Why does that happen is because whenever a gravitational wave is generated, it is because of the disturbance in the space-time fabric, and this disturbance in the space-time fabric can be created by the effect of a black hole, and no significant electromagnetic radiation can be generated by or observed when the observation can be done, thereby which proving the existence of a black hole. Then moving on to the second thing, what is binary star? A binary star, it is a star system consisting of two stars which are orbiting around their common barycenter. That is, two stars are there. Binary, the name indicates the number 2 itself. So binary star means two stars, and these two stars are rotating around their common barycenter. That is, the barycenter means it is the center of mass of two or more bodies that are orbiting each other, or the point around which they orbit. So here you can see the image of a black hole, and here you can see the image of a binary star. In the binary star, you can find two stars which are orbiting at a common point, that is barycenter, that is the center of gravity of, or sorry, the center of mass of the two bodies. Then moving on, what is meant by a neutron star? A neutron star is one of the stages. We have seen that a supernova will further progress into either a neutron star or a black hole. A neutron star, it is a collapsed core of a large star. Neutron stars are smallest and densest stars known to exist. They result from the supernova explosion of a massive star combined with a gravitational collapse that compresses the core part of the white dwarf to a point where the atoms become so compacted and so close together that electrons are violently thrust into their parent nuclei, combining with the protons to form neutrons. Thus, neutron star gets its name from its composition. What gravity has created is a super dense neutron-rich material called neutronium in a city-sized sphere. So, neutron star is the size of a city, small-sized city, and here it is called neutron star because what is happening is there is a collapse of the star because of intense gravitational force and also the density. And if you see the density of neutron star, it is one of the densest stars of all the stars in the life cycle of stars. And here what happened is, because of the intense pressure, because the electrons are fusing with protons leading to generation of neutrons, the star is named so. Then moving on, in 2017 Nobel Prize for Physics was awarded to Rainer Weiss, Barry Barish and Kip Thorne for decisive contributions to the LIGO detector and observation of gravitational wave. So that is the importance of gravitational wave, and it has significantly proved that the theory of relativity put forward by Mr. Albert Einstein is in fact true, and black holes do exist, as statement made by one of the greatest scientists, Stephen Hawking. With this, we conclude all the aspect of gravitational wave and totally covered in exam point of view. Thank you.